can go ahead, Amitesh.
Thank you so much, Peter, and Matthew and Vijay for the invitation and for helping organize. I really appreciate it. And I'm really excited today to tell you a story about knot polynomials, braid group representations, and class groups of number fields. And the main motivating question of the story that we're going to start off with is a question that we've all thought about. So it's a very fundamental question, and you can tell me if I'm lying after you see the question, but the question is, how good of an invariant is the Jones polynomial? So you can ask such a question about the Alexander polynomial as well, and much of this talk will apply there. But how good of an invariant is the Jones polynomial? So just to, fix notation and, general like principles. So what is a Jones polynomial? You have, say, an oriented link in S3. I'm going to try to draw the trefoil. And you have the Jones polynomial VL, which is going to be in Z adjoint root Q inverse. So a polynomial in root Q and root Q inverse. And this is an invariant of links, and we want to understand how good it is at distinguishing non-isotopic links. So let's try to make the question more precise. So we asked two particular sub-questions. So sub-question part A is, does the Jones polynomial of a knot detect the unknot? So does the Jones polynomial of a knot detect the unknot? Of a knot detect the unknot. So this is a famous open problem that has existed for a while, and it's quite interesting because there are non-trivial links with trivial Jones polynomial. So multiple components, but it's not known if there's a non-trivial knot with trivial Jones polynomial. And so this is part A, and part B is a bit more general, going beyond just the unknot. We can ask, how many knot/links are there with a given Jones polynomial? So how many knot/links are there with a given Jones polynomial? So, the answer to this question may be infinite in certain cases. It is infinite in certain cases. So we might try to make the question interesting and ask, how many knot/links are there with a given property and a given Jones polynomial? And maybe the answer is finite. And in that case, the finiteness result would be interesting. And maybe the finite number has an interesting interpretation. So this is kind of the main theme of this talk. So it'll be centered around this question and these two sub-questions. And the approach I'm going to take in this talk is a novel approach to these questions via braid group representations and class groups of number fields. So it's based on two works that I posted to the archive last year. And what I'm going to do is I'm going to go over that. But first of all, I'm just going to give you a high-level overview of how braid group representations enter the picture and help us to look at these questions. And then I'm going to go over like an accessible, introduction. So we're going to go over background, briefly, what are braid groups, what are braid group representations, and how they lead to, knot polynomials. And then I'll talk about my work. So it's designed to be super accessible, and please feel absolutely free at any stage, just interrupt if you have questions. I'm always very happy to answer questions. So just feel free to do that, or via Zoom chat, whichever you prefer. So let's just talk for a couple of minutes about the high-level overview, okay, just to see where braid group representations come in. So there is a representation of the braid group into the Hecke algebra Hn, whatever that is. Okay, we don't have to know what that is. It's just some representation of Bn. And there's a certain trace on the Hecke algebra called the Oceanu trace. And it maps into Z adjoint root Q inverse. Now, when I say trace, it's really, a normalized/weighted version of the usual matrix trace, which is adding up the diagonal entries. And what's interesting about this map, this trace of this representation, is that if I take, a link inside S3 and I put it in braid position, okay, this is something we'll also go over soon, but I put it in braid position if you aren't familiar, but we write it as the closure of some braid G, where G is in Bn. Then it's really cool that algebraically I can follow representation, follow G along to Hn, and then take the trace of that. And that composition is going to be the Jones polynomial VL of Q, of the link L. So you can define it algebraically, and this is in fact Jones's original definition of the representation of the polynomial. So what's really cool about this is that you immediately see that this representation is fundamental, Bn to Hn. And how faithful that representation is, or how one-to-one it is, or how small its kernel is, all different ways of saying the same thing, that's going to be intimately related to how good of an invariant is the Jones polynomial. Because if many elements of Bn map to the same thing in Hn, they're all going to have the same trace, and therefore you're going to have many different links with the same Jones polynomial. So we want to understand, is this representation faithful? And already this is quite an intricate question. So even in the case n equals 4, it's equivalent to the faithfulness of the Burau representation of B4, which is a long-standing question since the 1930s. And it's also known that if this representation is unfaithful, then the Jones polynomial of a knot does not detect the unknot. So there's a logical implication there that shows you that understanding the faithfulness of this representation is a necessary step to understanding the unknot detection question. So the first point I want to make is, so in my inner work I posted on the archive, it's called A Strong Characterization of the Entries of Burau Matrices of 4 Braids. I developed a theory to explicitly characterize the matrix entries of this representation. And that theory has 2 applications. So one application is it gives us a generic faithfulness result for this representation when n is 4. So I explicitly characterize a generic family of braids, in B4 that are not in the kernel of this representation. And this is, to my knowledge, the first such, general explicit characterization of a generic family of braids not in the kernel when n is 4. And second of all, because I explicitly characterize the entries of this representation, we can get an explicit characterization of the trace, and therefore a formula for the Jones polynomial of generic closed 4 braids and all closed 3 braids directly from a braid word. So this is forthcoming work. So the faithfulness result is already on the archive, and this explicit formula for the coefficients is forthcoming work. And, in general, it can be quite difficult to find the Jones polynomial from a braid word or a diagram because you have to apply an exponential number of Skein relations, but this formula is direct. So that's part A. So this is related a lot to the unknot detection question. And part B, to motivate where number theory comes into the picture and class groups of number fields. So there's a certain infinite interesting family of links called closed 3. Sorry.
One second. Are you saying you proved that B4 is not faithful for?
Oh, sorry. No, I said that I explicitly characterize the generic family of braids not in the kernel. So I showed the kernel is small, I guess, if you like. Thank you. Thank you. That's a great question. Thank you so much. Yeah, so basically, continuing on, so if we have the family of closed 3 braids, that includes the figure 8 knot, the hop link, the trefoil, all the standard simple knots that we know. The failure of Jones, so this is the next result, the failure of Jones to distinguish isotopy classes of closed 3 braids. To distinguish closed 3 braids. So this is a result. I posted. It's called A Novel Connection Between Integral Binary Quadratic Forms and Knot Polynomials. And the result says that the failure of Jones to distinguish isotopy classes of closed 3 braids is measured by class groups or class numbers of quadratic orders and quadratic number fields of the form Q adjoint root T squared minus 4. So what does this mean? So what's a special case of this is, for example, it's a known result that the Jones polynomial of closed 3 braids detects the unknot. This has been proven with some methods 20 years ago, as due to Stoimanov. And this connection here gives you another proof of that via number theory. So this specific relationship, if you consider the unknot, it basically says that the fact that the class group of Q adjoint root minus 3 has size 1, it's trivial, is the same as saying that Jones detects the unknot for 3 braid links. So there's a logical implication there where you can go from number theory to topology. That gives you a new proof of the result, or a new proof that the class group of Q adjoint root minus 3 is 1. So these class groups measure the failure of unique factorization to hold in some higher domains. In fact, Q of, the ring of integers in Q of root minus 3 is a Euclidean domain, so it's a UFD. Moreover than that, you can also show that because the class groups are finite, there are finitely many closed 3 braid links with a given Jones polynomial. So that also follows from the finiteness of class groups. That's also a known result, but it has a much different proof, and this is a proof using number theory. And finally, I'd like to mention that this relationship comes in a very precise manner. So Barry Mazur has an analogy that ideal classes in number fields should correspond to isotopy classes of links in space. And in this, to establish this result, I actually make the analogy very precise for this case. And I show that ideal classes in these quadratic number fields, really, you can associate explicitly links in 3 space. and in such a way that that association comes from actually the Burau representation of B3. So a very natural association between ideal classes in number fields and links in space, and makes a concrete connection between algebraic number theory and low-dimensional topology. So basically the overview I wanted to show you is just to show you that Braid group representations and class groups of number fields, how they are entering the picture. And what I'm going to do now is just give you an overview. We're going to go over Braid groups and Braid group representations and their relations to knot polynomials. So this is designed to be super accessible. And if you've already seen it, I hope that there may be some new perspectives, but just feel free to ask any questions. So I'll just take a quick pause now, and feel free to ask me if you have any questions so far. All right, so looking at braid groups, so what are the braid groups, first of all? So the braid group Bn is, topologically, it's a set of geometric n braids up to isotropy relative to endpoints. So what is an isotropy? So I'll go over this review in 5 to 10 minutes, and it'll get to like braid group representations. But what is a geometric n braid? So geometric n braid is you take Euclidean 3 space R3, you take the plane z equals 0 and z equals 1, and you draw endpoints on the plane z equals 0 and endpoints on the plane z equals 1. And a geometric n braid is just a picture where you're connecting the top points to the bottom points by n strands. And the strands have to continuously go upwards, but they can entangle with each other. So the entanglement is essentially the information encoded in a geometric n braid. And what's very interesting about geometric n braids is that they form a group under concatenation of pictures. So what I can do is if I draw one braid G and another braid H, I can literally stack one on top of the other and get a picture that goes from z equals 0 to z equals 2, say, and then I can rescale by half to get just a usual geometric n braid from z equals 0 to z equals 1. So there's a group law, and this group law makes Bn into a braid group, which is called, it's called the braid group. Now, braid groups were introduced by Artin in the 1920s, and he proved some fundamental results on them. Namely, he proved that they have a finite presentation, which is really cool. And you can really see the generators. So what is a finite presentation? Is we take the generators as follows. Sigma 1 is a generator. It's an element of the braid group. The first 2 strands are crossing and the remaining strands are vertical. And for this element, sigma 1, so it's a simple kind of element, we can also define sigma I, where all the strands are vertical except the ith and I plus first strands are crossing. That's sigma I. And finally, we go up to sigma n minus 1, where all the strands are vertical except the last 2 strands are crossing. So these sigma i's, if you invert them, you're just flipping the crossing. They form a generating set for the braid group. And that's something, if I give you a braid, what you can do is you can level out the crossing so 1 occurs on each level. And then you can see the word that represents the braid in this generating set. And so this is a generating set, but what's really cool is, in fact, it has a finite presentation. So the braid group is generated by sigma 1 up to sigma n minus 1 with the following relations. The first is the braid relation. Sigma I plus 1, sigma I is sigma I plus 1, sigma I plus 1 for 1 less than or equal to I less than or equal to n minus 1. And sigma I, sigma j equals sigma j, sigma I for absolute value I minus j greater than 1. So when I and j are far apart, they commute because the strands don't interact. And Artin proved this result. So this is a finite presentation of Bn. Now, why are we interested in this? Well, one reason, there are so many reasons braid groups come up. I'll only touch on low-dimensional topology in this talk, really. But one reason we're interested is that braids give you links very naturally. So if I write down a braid, so suppose I draw a braid, I'm just going to put it in a box here, G, and G is in Bn, you can write down a link from that. And this is what is called the braid closure operation. So what you do is you take that G, and it's a picture from bottom endpoints to top endpoints. You connect the top points by n parallel simple arcs that go like so. And by doing this, you form a closed picture, which is now, we call it G bar, G overline, and it's a link inside S3. And this process, is in fact surjective. So every link in S3 arises as a closure in this fashion. This is a theorem of Alexander. And in fact, there are infinitely many different braids that give you any given link. So an important question is, how do we relate, 2 different Gs that give you the same closure? How do we relate them? And Markov's theorem states that they're related by a finite sequence of moves called Markov moves. And what these Markov moves do, they're moves on the braids. They don't change the closure, but they change the braid. And so I'll show you one of them because it's very fundamental for this talk. It's the conjugation move. It's an algebraic operation. You have GH in Bn, and you consider the conjugate H inverse GH, and its closure is the same as the closure of G. So that's a result, and you can see this. That's really cool, is you can actually visualize this. So imagine what is H inverse GH in the braid group. You literally take G, you take H inverse, you take H, and you close it up. So you close it up by like these n parallel simple arcs. And what you see is that even though H and G may not commute in the braid group, you have the closed pictures. You can move the H inverse around and it can cancel off with H. And by doing that, so that cancellation happens in the braid group, you get back the picture that you would have gotten if you'd simply closed up G. So that shows you conjugation does not change the underlying link. And there's another move that changes the braid group. So this is within one braid group, but there's another move that goes to a new braid group, and it's very famous in low-dimensional topology. We see it in other contexts as well. It's stabilization. So if you take G inside Bn and you visualize G as being in Bn plus 1, just by adding an extra vertical strand at the end, you can multiply G with the last generator in Bn plus 1, which is sigma n, and get something in Bn plus 1. And that has the same closure as does G. So this is called stabilization. And if it exists, the inverse operation is called destabilization. And Markov's theorem states that any two braids that have the same link are related by a finite sequence of conjugation moves and stabilization/destabilization moves. And this is a really fundamental result. It allows us to really reduce studying links in principle to studying braids. And then, we have to now study braids, which has an algebraic structure, which is quite beautiful. So what I'm going to do now is I'm going to show you how the classical link invariants come from this kind of thinking. So Alexander polynomial, for example. But first of all, let's just abstractly think about how we can find new link invariants. What do we do? So we're interested in invariants of braids that don't change under these moves. So in particular, they shouldn't change under conjugation. So we're interested in functions on the braid group that are constant on conjugacy classes or have the same value for conjugate elements of Bn. And this is nothing other than a class function. This is just terminology. It's a class function on Bn. We're interested in these class functions on Bn, and we want them to be compatible as n varies, as the index n varies from different braid groups with stabilization and destabilization. But let's forget that for the moment and just focus on class functions on the braid groups. How do we do that? So there's a really cool way to find a class function on any group, and it's in classical representation theory. Take a group G, map it into a matrix group by some representation. And what you can do is, on a matrix group, you have many nice class functions. You have the trace, the determinant, and most generally, you have the characteristic polynomial. So you can compose a class function on a matrix group with this representation of G to get a class function on G. So what we're going to be interested in is finding interesting representations of the braid group and then deriving class functions and, by extension, link invariants from that. So that's what I'm going to do now. I'm going to explain how that works. So what I'm going to do is I'm going to now define or talk about the Burau representation. And we'll see how it gives you the Alexander polynomial. And what I'm going to do is I'm first going to give you a broad overview of Burau. So I'll sort of treat it as a black box, but tell you why we're interested in it, what its context in math is, what the history is, and then I will define it very precisely. So I just first want to just get a feeling for it before we define it precisely. That's what I'm going to do on the next whiteboard, and we'll find some interesting invariants of links from that. Okay, so what is the Burau representation? So we want to find representations of the braid group. What is a Burau representation? So let's just first say, what is its domain and range? So the domain of the Burau representation Bn is a braid group braid group Bn, and the range is it's mapping into gln minus 1 of z adjoint q to the plus minus 1. So every n braid is assigned an n minus 1 by n minus 1 invertible matrix with entries in z adjoint q to the plus minus 1. Now, maybe you don't like z adjoint q to the plus minus 1. It looks a bit weird. If that's the case, you can think of q as a transcendental. So you can map q to pi, and that would visualize z of q to the plus minus 1 as a subring of the real numbers. And so you can think of the Burau representation as just mapping, when mapping q to pi, for example, just mapping into gln minus 1 of r. And so you can think of it that way. And this representation was defined by Burau in the 1930s. And he proved that you can recover the Alexander polynomial completely from it. And I believe that was one of the motivations for defining it. And this is a really beautiful construction. So what is the construction? That if L is a link inside S3, you can find some braid, whichever one you like, that L is the closure of. So L is a closure of G. Let's say G is in Bn. And you can write down the Alexander polynomial of L up to a multiple of a power of Q. Okay, so up to an overall power of Q, you can write it as the following: the determinant of I minus beta n of G. So G is the braid which gives you L, divided by 1 plus Q squared plus dot 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 plus Q to the n minus 1. So this is a formula that Burau established. And what's really cool is that you immediately see the philosophy we talked about. You see that the numerator, this is the class function on the braid group. Because basically what we're doing there is we're taking the characteristic polynomial of the Burau representation of G at 1. We're evaluating the characteristic polynomial at 1, and that's the numerator. So it's a class function on a matrix group composed of the Burau representation. And then the denominator is just a normalization to ensure that this is compatible with stabilization/destabilizations. But this gives you the Alexander polynomial in terms of Burau. And you immediately see that how faithful is Burau is very intimately related to how good of an invariant is the Alexander polynomial. Because if many G's map to the same beta n of G, many links are going to, in principle, have the same Alexander polynomial. So what we are interested in now, we again tied into the faithfulness question of the Burau representation. And another motivation for studying the faithfulness question is that if beta n is faithful, you see that means the kernel is trivial. That's the same as saying the kernel is trivial. That implies, it's not an if and only if, but it's an implication. That implies that Bn is a group of, or it is an if and only if, but for other reasons I'll talk about. But Bn is a group of n minus 1 by n minus 1 matrices over the real numbers. Because you simply map by a Burau, and you can think of every Bn element of Bn as a n minus 1 by n minus 1 matrix. So that's another beautiful reason, because the braid groups have a very abstract algebraic structure. So it'd be really cool arithmetically in this way. So these are two reasons that initially motivated the study of this faithfulness question. And so let's talk about the history, what people have done on the faithfulness problem. So the progress is as follows. So it was in the late 1960s, so 30 or so years after the Burau representation was defined, that Magnus and Peluso showed that beta 3 is faithful. So this is the simplest interesting case, and this implies that B3 is a group of 2 by 2 matrices. So this is a result of Magnus and Peluso. And then it wasn't until the 1990s that, I believe it was because people generally thought it was faithful in general, but in the 1990s, Moody found a really beautiful argument that beta n is unfaithful for large n. So he proved that for n at least 9, beta n is unfaithful, and subsequently Long and Patton and Bigelow proved that for n at least 5 it is unfaithful. So the work of these people combined shows that beta n is unfaithful for n at least 5. And what remains is the case n equals 4. So is beta 4 faithful? And beta 4 is a map from B4 to GL3 of Z adjoint Q to the plus minus 1. And if beta 4 is faithful, that would imply, as mentioned on the previous whiteboard, that would imply that B4 is a group of 3 by 3 matrices. So if beta 4 is faithful, B4 is a group of 3 by 3 matrices, which is actually as best as you can do. You can't write B4 as a group of 2 by 2 matrices. So this is an interesting conceptual reason for studying this question. And in fact, it's a reverse implication as well. So if I tell you B4 is a group of 3 by 3 matrices, you can tell me that Burau 4 is faithful, because there aren't any interesting three-dimensional representations of B4 other than just Burau 4. You can scale it, or if you don't scale it, you have only reducible representations that split up into simpler pieces, one of which is one-dimensional. So in fact, there is a equivalence that beta 4 is faithful if and only if B4 is a group of 3 by 3 matrices. And there's another important reason for studying the faithfulness question. So this is one, and the one that we are talking about in this talk is related to the Jones polynomial. So in the late 1990s, Bigelow conjectured that if Burau 4 is unfaithful, then the Jones polynomial of a knot does not detect the unknot. So this was a conjecture, and let's explain why he was interested or why he made this conjecture. So the motivation is the following, that if you think about this representation at the beginning, Bn to Hn, where the Jones polynomial is the trace of it. When in general, it splits into irreducible pieces parametrized by Young diagrams for n, just like the irreducible representations of permutation groups. So that's really beautiful. And more than that, when n is 4, the only potentially faithful piece that can exist is Burau 4. So if Burau 4 is unfaithful, then this representation would become unfaithful when n is 4. And then it's conceivable that if you take something in the kernel, you could somehow find a non-trivial knot with trivial Jones polynomial, because it's just a trace of this representation. But there is something that has to be done there. And it was a few years ago that Ito proved that this is true. So he proved that if this representation is unfaithful, so in particular, if Burau 4 is unfaithful, then there is a non-trivial knot with trivial Jones polynomial. So that's a logical implication that goes from studying the faithfulness question to this Jones polynomial. But there's a question of the other direction. So Bigelow also writes in his article in the 90s, like he doesn't know that if there's a concrete connection the other way, that if this representation is faithful, does it say anything about the Jones polynomial? And part of the point of this talk is to show you that there is an approach, not logically, because just knowing that this is faithful doesn't necessarily tell you anything about the matrices or the traces of them. But in the work I explained earlier, I explicitly characterize the entries of the matrices, which then not only leads to this generic faithfulness result, but also leads to studying the Jones polynomial. So in particular, I can explicitly characterize a new generic family of closed 4 braids where the Jones polynomial detects the unknot using this explicit characterization of the entries of the matrices. So this is just a general overview that shows you how the Burau representation fits in. There are many other applications, but this is what we'll focus on in this talk. So I'm just going to take a brief pause, and if there are any questions, feel free to ask me before I kind of get on to the next topic.
Yeah, sorry, I missed something. So you're studying the beta 4, the 4-stranded Burau representation. So you're saying that that's faithful if and only if the Hecke algebra representation is. Was that implied there? Okay.
Yes.
Why is that? Sorry, I just missed how the connection between the Hecke algebra representation and Burau.
That's a great question. So the Hecke algebra representation splits up into irreducible pieces corresponding to Young diagrams for n.
Oh, okay.
And the only faithful piece in the case, only potentially faithful piece in the case n is 4 is Burau. So there's an if and only if there. And in general, Burau faithfulness is sufficient for the Hecke algebra faithfulness, but not necessary. There are other irreducible pieces that could be faithful.
Okay, thanks. Sorry, you said that.
No, thank you so much. That's a great question. Thank you. Yeah, so any other questions? All right, so yeah, just feel free to ask anytime, and even by Zoom chat if you feel comfortable. So what I'm going to do now is I'm going to define the Burau representation, and then I will study the faithfulness question. That's going to be the rest of the talk. I'm not going to pretend to go through all the intricacies, but just want to give you an overview and an introduction so you get a feeling for what's involved. But first, let's try to define the Burau representation. So I like to, whenever we think about, braid groups or math in general, it's always nice to look at the simplest example, and lots of phenomena come from there. So let's just start off with the braid group B3. So B3 is the simplest interesting braid group. It has 2 generators, sigma 1 and sigma 2, with a single Artin relation. 1, 2, 1 is 2, 1, 2. And so this is a braid group B3. And how do we find, suppose I ask you, how do you find a representation of B3? So what you're going to tell me is basically we need 2 matrices, 1 for each generator, right? So they are mapping to those matrices. And for the representation to be well defined, we want the matrices to satisfy the braid relation, ABA equals BAB. So that's what we're after, 2 matrices A and B, where ABA is BAB. And what's really beautiful about this is everyone who studied linear algebra has seen such matrices. And they occur, in the very beginning in a way. They're the following: the elementary matrices A equals 1, 1, 1, 0, 1, and B equals to 1, 1, 0, 1. And what's really cool about these matrices is if you pre-multiply them with a 2 by 2 matrix, you're just doing a row operation to that 2 by 2 matrix. So the fact that any 2 by 2 integer matrix of determinant 1 can be row reduced to the identity without any scaling operations implies that A and B generate all the 2x2 matrices of integer matrices of determinant 1, which is just SL2 of Z. So SL2 of Z, these are matrices in SL2 of Z. They generate SL2 of Z, and there is a finite presentation. So they do satisfy this relation ABA equals BAB. And they also satisfy the relation AB to the 6 is the identity. And that's an extra relation. So what that means is that this map that sends sigma 1 to A and sigma 2 to B is not faithful because there is an extra relation on the right-hand side. However, we can actually explicitly write down a short exact sequence and find the kernel. And I'm going to write that down on the next board. So we can say the kernel is just generated by this extra relation. So you have this map B3 to SL2Z, which we defined. It's surjective. And the kernel is just generated by this AB to the 6, which is sigma 1, sigma 2 to the 6. And that's a short exact sequence. And what's really cool about this is earlier I mentioned that whenever you come up with a Braid group representation, you may be able to find a link invariant. So what about this Braid group representation? What link invariant do we get? So we want to find a class function on SL2Z. Let's try the trace. The trace is a natural one. The trace of this representation B3 to SL2Z is actually nothing other than the special value of the Alexander or the Jones polynomial at -1. And the absolute value of that is the well-known knot determinant invariant for knots and links. So this representation already gives you that determinant invariant and the special value of these Alexander and Jones polynomials. And then, we're sort of seeing how Braid group representations give rise to link invariants. And now we want to make a better link invariant. How do we do that? We try to make the representation faithful. So how do we make the representation faithful? We need to get rid of this kernel. And here's a cool way, that you can see this is by taking a quantum deformation of the matrices A and B. So instead of taking A and B, we take these matrices AQ and BQ, -Q, -Q0, 1, and BQ is going to equal to 1, -1, -Q0. And if you specialize Q is -1, you get back A and B. So it's a quantum deformation in that sense. And what's interesting is AQ and BQ have determinant -Q. So that means no non-trivial power of AQ, BQ to the 6 can ever be the identity. So this representation now, gets rid of the kernel, and it's now going to be faithful. And this is actually nothing other than the Burau representation of B3. So this is a quick, sort of a sketch of an argument that Burau 3 is faithful. There are many in the literature. This is one. I haven't seen it written down, but there are several different ones. It gives you a feeling for how Burau 3 is defined. And we can, in fact, generalize this. So that's the cool thing. You start with B3. Let's now try to make a representation of B4. And you do it in the natural way. You add an extra dimension and kind of use very similar matrices. So I'll write that down on the next board. So this is going to be the next one. You can write down the Burau representation of B4. And it's very similar to the Burau representation of B3. So we simply write it down as follows. I'll show you the matrices. So sigma 1 is going to map to -Q, -Q, 0, 0, 1, 0, 0, 0, 1. And sigma 2 is going to map to 1, -Q, -Q, -1, 1, 0, 0. And finally, sigma 3 is going to map to 1, 1, -1, -Q, 0, 0, 0, 0. Okay, so this is the Burau representation of B4. And I just want you to notice that you see the Burau representation of B3 lurking. If you look at the top left-hand block, for example, that's just the, sorry, that should be, one should be 1. I will just, it's not going to be super important, but I'll just make this -Q. So that's going to be the Burau representation. So you see the top left-hand block is going to be exactly looking like the Burau representation of B3. So this is just generalizing one dimension higher. And it's already so cool, right? That, okay, so B3, we saw it's faithful. We kind of got the idea. But the faithfulness of this representation has been open for 100 years. So it's already gets somehow extremely complicated once you jump one dimension higher. But this is what we're going to discuss in the rest of the talk, how to study the faithfulness question for this representation. And what I want to do is, as I said, I'm not going to be able to go through all the intricacies, but I want to give you a general feeling for how we approach this problem. And that's what I'm going to do. And then I'm going to state my main result and basically end the talk. So that's going to be the last 20, little bit less than 20 or so minutes. So let's get to that. Any questions so far? All right, so let's talk about the faithfulness problem. So this is a general principle. How do we study the faithfulness of any representation of any group? What do we do? So, let's just kind of make it, sort of dumb it down. We want to show that if you have a non-identity element in B4, you want to show that the Burau matrix of G is not the identity. That's it. That's what faithfulness is. Now, how do you do this? So if I give you a G in B4, you might try to write it as a word in the generators, and that's the way to think of it. And then we can multiply out the matrices of the generators that were written down on the previous board. And then we would be able to compute beta 4 of G. So we need to find a word representing G, and we need to know when such words are non-trivial. When you give a word in the generators, when is it non-trivial? That is nothing other than the word problem in the Braid group. So we need to solve the word problem. And if you think about it, if I did tell you this representation is faithful, you would have a solution to the word problem. Any two words, you just plug in their matrices and compare them. So it's necessary to solve the word problem in a group before kind of understanding a faithfulness question. But even more than that, you want to try to find a nice product expansion of every element of B4. So there are many different words representing an element. You want to choose a nice one where you can compute the matrices easily. You don't want to go through any one. So what we want a canonical form for elements of B4. And this is really a question about the algebraic structure of the Braid group. And that's like any, generally, faithfulness question. You want to understand the algebraic structure of the group and then the combinatorics of the representation. So first we focus on finding a canonical form in B4. And what I'm going to tell you is it's a fundamental canonical form due to Garside. It's really beautiful. I'll give you a quick overview of what that is and motivate it from the perspective of this question. So what is the canonical form due to Garside? So suppose, as I said, a word can be quite complicated. I can write down a word like this for you. Sigma 2 power minus 3, sigma 1 power minus 5, sigma 2 cubed. And this looks like a nightmare. If I wanted to calculate the matrix for this word, it would be very complicated. I have to multiply them out. I have to have negative powers. So I don't want to deal with that. So what I want to do is I want to write it down in a way which is easy to compute. And Garside, a special case of his result is that you can any word like this, you can write it as a word where you collect all the negative exponents to one side and all the positive exponents to the other side. So it's a product of negative powers of the generators and then positive powers of the generators. And another way of saying that is it's tau inverse sigma, where sigma tau in Bn, this is true for all n, so Bn plus are what are called positive braids. So a positive braid is a product of positive powers of the generators. And so tau inverse is going to be a product of negative powers of the generators. And so this is a representation that Garside established. Garside actually established a lot more than this. He showed that you can think of tau inverse as just being a power of delta, the Garside element. So he proved that there is a special element delta, which we'll talk about, where you can take the tau inverse to just be a power of this delta. And this already makes the faithfulness question a lot easier to handle. I'll give you a quick idea of what delta is, what power of delta is. It's really cool. So delta, you can write it in B4 as a word, and that's not maybe very enlightening unless you work with the Braid groups actively. But another way of thinking about it, which is very visual, is thinking about delta squared, which you can think of the Braid group Bn, and this is another cool way of looking at the Braid group. You can think of it as the mapping class group of the n times mark disk. All orientation preserving homeomorphisms of the n times mark disk that are the identity on the boundary and permute the mark points. And under this description of Bn, you take delta squared is a full twist with respect to the boundary circle. So how you can visualize that, as always with mapping classes, is you imagine arcs inside the domain. And what a full twist does is it's going to twist the arc. If it touches the boundary, it's going to twist the arc once, like so. So this is what delta squared does to arcs. And so you can see what it does in general. And this is because it is a full twist with respect to the boundary, it commutes with every braid because every braid acts as the identity on the boundary. So in fact, delta squared is central in Bn. It's a very special element. And one can even show that center of Bn is generated by delta squared. This was proven by Garside. So you have this really special element delta, and delta squared has this really special property. And Garside's theorem basically tells you that any element of the Braid group can be factored in this really nice way. So this is a theorem due to Garside. that any element delta can be any element of the braid group. So if G is in Bn, then we can write G as a product of delta to the k sigma, where k is an integer and sigma is in Bn plus, is a positive braid. Product of positive powers of the generators. Okay, so that's the result. And okay, so that's really cool, but what does it tell us about the faithfulness problem? So already it tells us a lot. So let's just, first of all, let's replace k with minus k, just for aesthetic purposes. It's the same thing because k is an integer. So let's just say k minus k. Now we see that beta 4 of G is not the identity if and only if beta 4 of sigma is not beta 4 of delta to the k. Okay, so what does that mean? It means that beta 4 is faithful if and only if the following statement is true, that if sigma is not equal to delta to the k, then beta 4 of sigma is not equal to beta 4 of delta to the k. So the algebraic structure of the braid group has told us something, has reduced the faithfulness problem somehow for us. This is typical in these kinds of questions. And we just need to find the Burau matrix of positive braids. So we don't have to invert any of the matrices, just multiply them out, which is really cool. And what's even cooler is that beta 4 of delta to the k is a very special matrix. It has a single non-zero entry in each row. And you can kind of see this, conceptually. Delta squared is central, and central elements act as scalars times the identity on irreducible representations. If you remember Scher's lemma in representation theory. So that's like a conceptual reason to see that, but you can even compute that delta to the k for all k has a single non-zero entry in each row if you take beta 4 of it. So now what we want to show, what we can reduce faithfulness to, is showing that if sigma is not equal to delta to the k, then there are multiple non-zero entries in a row of beta 4 of sigma. There are multiple non-zero entries in a row of beta 4 of sigma. So we want a method for producing non-zero entries inside beta 4 of any positive braid that's not delta to the k. That's the strategy. That's now combinatorics of beta 4. And that's what I'll try to talk about at the end. Just before doing that, I will state my main result. So this is kind of the algebraic structure, but I want to now state my main result on Burau 4 very explicitly. So that's what I will do here. So to state it, I need one more definition, which is we talked about finding a canonical product expansion of every braid. We write it as delta to the k sigma. Then we can find a canonical product expansion of every positive braid. So if you have a positive braid, a product of positive powers with no inverses, something like this, you can have two different product expansions. This is a elementary example. 1, 2, 1 is 2, 1, 2. It's an Artin relation. How do I choose one canonical one to work with rather than dealing with all of them at once? So what I can do is, and this is a really cool trick, is you take 1, 2, 1, you write down the number you get by reading up the indices. So you write down 121. Okay, and for any other product expansion, you write down the number as well, 212. And you choose the product expansion where the number is smallest, and you say that's the canonical product expansion. And we're going to call that the minimal form of a positive braid. It's a canonical form for the positive braid. And it's a really, it's an interesting exercise. If I give you a random product expansion of a positive braid, how do I find its minimal form, or how do I tell if it's in minimal form? Sometimes you can apply these relations and increase the number before ultimately decreasing it. But in fact, there is a complete characterization of when these are in minimal form. And it's a fun exercise. It's also lemma 2.4 in my paper if you want to have a look, but it's cool to just play around with them. But once we have this canonical product expansion of every positive braid, I can state my main result. And I'm going to do that in the next whiteboard. So this is essentially the main theorem of my paper. It's the following, that if you take G in B4, okay, so we can write it in Garside normal form. So let's just do that. We can always do that. If G equals delta to the k sigma is in B4, this is the Garside normal form. And if either k is at least 0, so if either k is at least 0 or sigma is a normal braid, okay, so this is terminology that I will define. I haven't defined it yet, but I'm just going to state the result taking, okay, what is normal braid? So sigma is a normal braid or a weakly normal braid. So this is even more general than normal braid. So under these conditions, you can say that G is not in the kernel of the Burau representation. So if k is non-negative, it's never in the kernel. That's not difficult. That's relatively straightforward. But if k is negative, you have this mild condition on the braid. So almost all braids are normal or weakly normal. I will show you what it is. But almost all braids are normal or weakly normal. So you put this mild condition on sigma, you can rule out G from being in the kernel of beta 4. So that's the main result. But now I need to tell you what a normal braid is. And I'll show you why it's generic. So the definition of a normal braid is as follows, that if sigma is a product, write a positive braid, right, as a product of the generators. So I'm going to write it in the following way, just a product of powers of the generators where all the exponents are positive. Then we say that sigma is normal if the following condition is true for each p less than n. Okay, so each p less than n, we have the following condition. There are actually two conditions. I will only state one because the other is similar. It's also in my paper, but I'll state one to give you an idea. So the condition is that if AP is 0 and BP is 1, then CP should not be 2. That's the condition. So essentially, AP, BP, CP are exponents in the expansion. They can be any non-negative triple, any triple of non-negative numbers. We just want to rule out 0, 1, 2. So you can see that generically, a positive braid is going to be normal. And in here, this is the minimal form. So we're choosing the minimal form of sigma. And we're requiring that, we have this condition that this specific triple 0, 1, 2 does not occur. It's a generic condition. And then we say sigma is normal. And delta to the k sigma is never in the kernel. So that's one result. But then you might ask, what about if this condition fails? And even then, it's generically true that delta to the k sigma is not in the kernel. And this should give you an idea of what I meant when I said, they're like very long strings in the braid. Unless they're very long, highly constrained strings, you can rule it out from being in the kernel. And this is what weakly normal is, to give you an idea. So if AP, so we have something in the braid that looks like this, just to visually show you. And if AP is 0 and BP is 1 and CP is 2, so this is the failure of normality, then what this is going to look like, it's going to look like sigma 2 to the CP minus 1, sigma 3, sigma 2 squared. So it's just going to reduce to this. And this is the bad thing that we want to rule out. Now, suppose this happens. It is still true that sigma is weakly normal, so long as the following doesn't happen. So let's just say CP minus 1 is 100 for the sake of argument. Okay, works for any value of CP minus 1. Unless there is a highly constrained string directly following this, and the string has to look something like sigma 3 squared, sigma 2 squared, etc., 98 squares that alternate between sigma 3 and sigma 2. Unless there is that string, you can say sigma is weakly normal. So if there are more than 98 squares, less than 98 squares, one of the sigma 3s is a sigma 1, even just one of them. Or one of the sigma 3 squared is sigma 1 power something, sigma 3 power something. Everything's fine. Sigma is weakly normal, and delta to the k sigma is never in the kernel. So it's just these very highly constrained strings you have to handle. So, so my main result basically reduces the faithfulness to studying these highly constrained strings and rules out almost all braids from being in the kernel. So that's there. And what I will do in the last, just a couple of minutes is just give you a quick idea of how we kind of find entries in these braids, in the Burau matrices of these braids. There are more questions I can answer afterwards, but that will end the talk. So let's
ask a question about
yes,
the
yes,
ones.
please.
So
Yes.
for these that you've shown are not in the kernel, I mean, if it's a positive braid, if k is not negative, then then you can argue that the Alexander polynomial is non-trivial, and so that would show that it's. I mean, do you know that? Are some of the ones that you've shown are not in the kernel? Do you know that the Alexander polynomials are trivial?
Oh, so are you talking about yeah, I guess the k at least 0 here is kind of like a trivial, I mean, yeah, I say if it's a positive braid, it's just, yeah, sorry.
Yeah, but I can imagine, are some of the ones that are not positive braids, for which maybe you don't, I guess, are any of the members of your family, do they have trivial Alexander polynomial?
Oh, any of them. I guess it's a generic family. So if all of them had trivial Alexander polynomial, that would be weird, I guess.
Yeah, I mean, probably most of them don't. I mean, the ones with
Yeah.
k greater than or equals 0 don't, but
True,
I
yeah.
mean, I just don't know if any of them do.
Oh, I see. So you're asking
this is about Burau, but the weaker invariant is just the Alexander polynomial. And so for some of them, that weaker invariant will show that they're not in the kernel, but I'm just wondering.
How do you, I see, how do you compute though? How would you compute the Alexander polynomial? Like, would that be?
Well, I don't know. I mean, I don't know in general for your family. I mean, I just know that like I have some other secret methods or whatever, you know, more geometric to understand the case when k is non-negative.
Right.
But
yeah,
you know.
Yeah, I see. Yeah, I guess when k, okay, that's interesting. Yeah, I mean, when k is negative, I guess, yeah, I would imagine it's hard because it probably includes almost all like the closed four braids. So
yeah,
I think it would be harder to compute Alexander than Burau, but yeah, but I'm interested to know your secret method, I guess.
Okay, cool, thanks. sorry.
No, that's a great question. Thank you for mentioning that. Yeah, so just just quickly, like I just wanted to mention like how the entries of the matrix can be computed. So basically, there's this mental model where you can see the entries of the Burau matrices of long strings without really going through the matrix multiplication. And that's just what I want to show you. And just to give you a quick idea of that, beta 4 of sigma 1, for example, is minus q 0, 0, 1, 0, 0, 0, 1. We can represent this by a picture. So the picture looks something like this. The picture has these edges and these weights. So I write it as so. What does it mean? So what do I mean when I draw this picture? I mean that the ij entry of this Burau matrix is just the weighted number of paths from I to j, going from top to bottom. Weighted number of paths from I to j, going from bottom to top. So for example, if you look at 1 to 1, there's a single edge that has a weight of minus q, and that's the 1, 1 entry of the matrix. And similarly, there's a single edge that goes from 2 to 1, that's minus q, that's the 2, 1 entry of the matrix. So you can represent the matrix by a picture, and matrix multiplication comes from stacking these pictures. So what's really cool is if I draw the picture for sigma 2, which looks something like this. I'm just kind of giving you like a quick overview. So if you draw the picture for sigma 2, which looks something like this and represents beta 4 of sigma 2, we can find beta 4 of sigma 2, sigma 1. So I'll do that on the next whiteboard. Suppose you write down beta 4 of sigma 2, sigma 1. You just want to stack the pictures and count paths. So here you stack the picture for sigma 2, and then you take the picture for sigma 1. And what you see here is that for sigma 2, you have something like this, minus q, minus q1, and minus q, 1, 1. And suppose you're interested in finding the 1, 1 entry. Okay, 1, 1 entry of this matrix, you stack the pictures, you see there are two paths that go from 1 to 1. They're both sides of a triangle. So one path goes straight up, and it's minus 1 and minus q. Its weight is going to be the product, which is plus q. And the other path goes diagonally, and its weight is the product. Sorry, that should be, I believe that should be 1. Sorry. So that's 1. The other one is this weight has minus q. And the other path has weight plus q. So when you draw these out, you see that there are two paths, they're canceling weights, and the triangle kind of acts like a null homotopy. So you can see that they're canceling weights, and that immediately tells you the 1, 1 entry is 0. And what's really cool is when you have really long strings, you just want to avoid the triangles to create non-canceling terms. So that's the last thing I will show, that if you have like a string like sigma 1, sigma 2, sigma 1 squared, sigma 2 squared, sigma 1, and I can draw it like this. So sigma 2, sigma 1 squared. So I'm going to stack the pictures literally one on top of the other. You have these triangles, and you just want to avoid them to avoid your path from canceling. And this is an unstable situation that you can't. So for example, if you start at the vertex 1 here, you can't really avoid the triangles. If you go up, you have to go up again and you stay with the triangle. So the only thing you can really do is you can go diagonally. And then to avoid the triangles, your path is completely constrained. And you have to force it to be this. So this actually shows immediately there's a unique non-zero entry in the first row. But then on the second row, you can avoid the triangles. You have more freedom because you're not starting at 1. So I'm kind of being sketchy here, but the basic idea is just to show you, like, even for very long strings, you can quickly find non-canceling terms by just constructing paths that avoid the triangles. And there are other kinds of models of cancellation that exist, but they're described in my paper. But I will end the talk here. If there are more questions, I'll be very happy to answer. And there were great questions in the talk as well. So thank you so much for listening, and really appreciate it.